Example 6.2. The current of the inductor is 0 for 0, 0 minus, and at 0 plus it's 4 sine 2 theta, where the units of time and current are seconds and amps. Determine the power absorbed by the inductor and the energy stored in the inductor. So somewhere along the line, we're going to have to use this hint here. But let's start off with the beginning here. So the power of passive elements differ between resistors versus storage elements. And when I say a storage element, I mean a capacitor and inductor. Resistors are linear, which really tells us that their power of a resistor is written VR times IR, and that's typically we write the power, but because it's linear, we could come in and we can replace using Ohm's law, where I could look at the voltage across the resistor squared divided by R, or it's IR squared. We cannot do this with storage elements. Because they are nonlinear. So that means if I talk about the capacitor of a capacitor, I have to write it as VCIC. And if I have the power of an inductor, I also have to have the voltage times the current. But in this situation, we can rewrite the voltage so that it looks something like this. So then it's going to be L di dt. Or I can write this, cleaning it up just a tiny bit, the inductance times the derivative of the current. And because this is nonlinear, we can't do what we did with the resistors. So now let's look at the inductive power. So the inductive power is what we want to calculate. So from the power equation, we know that the power of the inductor as a function of time is then going to be L IL of t times the derivative of I. But we know what the inductance value is. We see here is that's a 5 Henry inductor. And we know that the current is 4 sine of 2t. Then I got to take the derivative of the 4 sine 2t. And if I do that, right, I'm going to get a cosine of 2 theta, of 2t. So I'm going to get 4 times 2, which is 8. 8 times 5 is 40. Times 4 should give me 160 sine of 2t cosine of 2t. So what we do here is that here's where we want to use the hint, because to make the integration of power easier, use the given trig identity. Okay, so what we'll do here is that if you look at the trig identity, you could see here is that it's 2 cosine A sine B, and then I'm going to get the two sine functions where I add and subtract the arguments here. So here I go. So what I'm going to do here is I'm going to pull out a 2. So here's the power of the inductor. I'm going to pull out a 2. So then that's going to give me 80. And then you could see here that I'm going to have 2 sine of 2t, cosine of 2t. And then here's where I'm going to apply the identity here. So right here comes in the identity. So if I do the identity right there, look what I'm going to do. I'm now going to have 2 sines where I add and subtract them. So then this gives me 80. Then I can write this as sine where I add them plus the sine where I subtract them. And clearly this guy's 0 right here. Sine of 0 is 0. So that means I can now write my power equation as sine of 4t in units of watts, or the power as a function of time. So to get the inductive energy, I just have to integrate this. So now I'm going to come in, I want the inductive energy. So the energy stored in the inductor is in the B field. So this is how we define the energy as the integral of the power of the inductor times time. So then if I plug this guy in here, you're going to see that I'm going to have 80 from 0 to t. And then I'm going to have sine of 4t dt. And so when I integrate this, note that if I integrate sine, I'm going to get cosine. So then I'm going to get, so look what I'm going to get. So if I integrate sine, I'm going to get negative 1/4. So I'm going to get 80 times negative 1/4. And then I'm going to have cosine of 4t from 0 to t. Now note 0 of cosine is 1, but I'm going to have a negative, so I'm going to get a positive at the end. So then this tells me here that this guy's going to be 21 minus cosine of 4t in units of joules, and that's the energy stored as a function of time for the inductor.